This video is audio content only. It does not contain any video footage or images. If you are expecting visual content, please be aware. This is intentionally provided in an audio-only format. We recommend listening to the audio rather than watching the screen. Thank you for your understanding. Welcome to The Shrinking Giants. When we picture dinosaurs, our minds often conjure images of colossal beasts. But what if their immense size is only half the story? This narration challenges that popular image, revealing a surprising evolutionary secret: miniaturization. Discover how many dinosaur lineages, far from growing ever larger, strategically shrank over millions of years, unlocking new ways to survive, thrive, and even pave the way for birds. Get ready to explore the tiny titans of the prehistoric world. Chapter 1. The Shrinking Giants, a New View of Dinosaurs. When we picture dinosaurs, our minds often conjure images of colossal beasts, the towering long-necked sauropods, or the formidable Tyrannosaurus rex shaking the ground with every step. Popular culture has ingrained this idea of dinosaurs as synonymous with gigantism, creatures of immense scale that dominated prehistoric landscapes. But what if I told you that this popular image only tells half the story? Recent scientific endeavors are painting a far more nuanced picture of dinosaurian evolution, one where being small wasn't just a quirk, but a powerful, often crucial, strategy for survival. This is the story of dinosaur miniaturization. Miniaturization in the context of dinosaurs isn't simply about being small-bodied, like a lizard or a bird today. Instead, it describes a profound evolutionary pattern where entire lineages, stemming from larger ancestors, underwent a significant and sustained reduction in body size over millions of years. Imagine a family tree where, instead of growing larger with each generation, some branches consistently trended smaller, sometimes reaching sizes comparable to modern chickens or even less than a kilogram in weight. This wasn't a random occurrence. It was a strategic adaptation, a testament to the diverse ways life finds to thrive amidst changing environments and intense ecological pressures. It's a phenomenon distinct from island dwarfism, which often results from isolation and limited resources on islands. Instead, this miniaturization occurred independently across multiple dinosaur groups, underscoring the widespread selective advantages it offered. The most prominent examples of this downsizing trend emerged during the Cretaceous period, roughly 90 to 66 million years ago, the final chapter of the dinosaurs' reign. This era was a time of dynamic global change. Continents were drifting apart, sea levels fluctuated dramatically, and terrestrial ecosystems were rapidly transforming with the rise of new plant life, particularly flowering plants. This period, often referred to as the Cretaceous Terrestrial Revolution, created a complex tapestry of new challenges and opportunities. For many dinosaurs, shrinking proved to be an ingenious solution amidst these profound ecological shifts. Why would a dinosaur choose to shrink? The reasons are as varied and intricate as the ecosystems they inhabited. For one, miniaturization opened up entirely new ecological niches that were simply unavailable to their larger relatives. Picture dense, tangled undergrowth in burgeoning forests, or the intricate network of burrows beneath the surface. Larger dinosaurs couldn't navigate these microhabitats, but their smaller cousins could. This allowed them to exploit resources like insects, seeds, and fruits, food sources that were too small or too scattered to sustain a massive herbivore or carnivore. A well-known example is Compsognathus, a small, agile theropod that likely hunted small prey in dense vegetation. The ability to tap into these alternative food sources provided a significant advantage, especially during times of ecological stress or scarcity. Beyond access to new food, smaller body sizes offered significant metabolic advantages. A smaller dinosaur required less absolute food intake to fuel its bodily functions, making it more resilient during periods of resource scarcity, which were often characteristic of the Cretaceous with its fluctuating environments. This metabolic efficiency could mean the difference between survival and starvation. Research into growth patterns preserved in the bones of these miniature dinosaurs suggests that many reached sexual maturity more quickly than their larger relatives. This accelerated development allowed for faster reproductive cycles and, consequently, more rapid population growth, increasing their chances of surviving localized environmental changes. Furthermore, in the warm Cretaceous climates, smaller bodies could dissipate heat more efficiently, potentially offering thermoregulatory benefits. These combined metabolic benefits exerted a strong selective pressure, repeatedly favoring smaller body sizes across multiple dinosaur lineages.
Predator avoidance also played a crucial role. In a world still dominated by formidable carnivores, being small offered a distinct advantage in evasion. Miniaturized dinosaurs could move with greater speed and agility, darting into hiding places inaccessible to larger predators. Fossil evidence indicates that many small species evolved proportionally larger eyes relative to their skull size, suggesting enhanced visual acuity and possibly nocturnal habits, allowing them to avoid the larger daytime hunters. Some even developed gliding or limited flight capabilities, offering escape routes unavailable to their ground-dwelling relatives. For instance, the small feathered Microraptor is a prime example of a dinosaur that used its diminutive size and 4 wings for gliding, likely to escape predators or navigate arboreal environments. These adaptations collectively boosted their chances of survival in ecosystems where the biggest beasts were often the most vulnerable targets.
Perhaps the most profound and enduring example of miniaturization's evolutionary power lies in the lineage directly ancestral to birds. This theropod branch underwent a sustained miniaturization across 50 million years and at least 12 consecutive evolutionary branches. This prolonged shrinking trend was not merely a survival tactic. It was a fundamental evolutionary pathway, facilitating the development of skeletal adaptations 4 times faster than other dinosaurs, and leading to the evolution of paedomorphic skulls, essentially retaining juvenile skull features into adulthood, with reduced snouts but enlarged eyes and brains. This long-term continuous reduction in size was a critical enabler, ultimately paving the way for the origin of powered flight and the unparalleled diversification of birds, demonstrating miniaturization as a foundational strategy for entirely new forms of life. The phenomenon of dinosaur miniaturization, far from being a mere footnote in their evolutionary saga, emerges as a powerful and recurring strategy that allowed these magnificent creatures to adapt and survive in ways we are only just beginning to fully appreciate. This intricate interplay of environmental pressures, ecological opportunities, and developmental shifts led to a surprising diversity of small-bodied dinosaurs. In the chapters that follow, we will delve into some of the most groundbreaking recent discoveries that showcase these uniquely adapted miniature dinosaurs, explore the profound developmental mechanisms, beyond just selective pressures, that enabled such dramatic changes in body size, and further examine how miniaturization allowed them to conquer entirely new ecological niches.
Chapter 2: Tiny Titans – Groundbreaking Discoveries. Paleontology is a field of constant discovery, and recent finds are not just adding new names to the fossil record. They are fundamentally reshaping our understanding of how these ancient creatures adapted their bodies to survive, often through unexpected and ingenious forms of miniaturization. Today, we're diving deep into some of these groundbreaking discoveries, revealing the unique adaptations of miniature dinosaurs that allowed them to thrive in a world often dominated by giants. One of the most captivating stories to emerge from recent research revolves around a peculiar group of bird-like theropods called alverosaurids. For many years, the prevailing scientific narrative suggested a straightforward evolutionary path for these dinosaurs. They steadily shrank in size as they specialized in a diet of social insects like ants and termites. The image was clear: a small, stubby-armed creature, perfectly designed with an oversized thumb claw for digging into insect mounds. This tidy hypothesis linked their miniaturization directly to this dietary shift, suggesting they got smaller to become more efficient anteaters. However, a remarkable discovery from the Candeleros Formation in Argentina has dramatically rewritten this story. Paleontologists unearthed a nearly complete skeleton of one of the smallest Alvarezzosaurs ever found, a species estimated to have weighed a mere 700 to 900 grams and measured about 70 centimeters in total length, more than half of which was its tail. This creature, roughly the size of a modern chicken or crow, was named Anachetri, meaning slender ankles, in the local Mapudungun language, a nod to its agile build. What made this fossil so extraordinary was that even though it was a sub-adult, confidently identified as over 4 years old at death and likely female due to the presence of medullary bone, a temporary tissue associated with egg-laying in modern birds, its anatomy profoundly challenged the established narrative. This tiny dinosaur, a coelurosaur sharing a branch with Tyrannosaurus rex, did not possess the extreme specializations for ant-eating that its later relatives would. Instead of the robust, short forelimbs typically associated with digging into termite mounds, Anachetri sported comparatively long forelimbs, measuring an impressive 61% of its entire hind limb length. While it did have the characteristic three-fingered hands with a robust first digit, a hallmark of its group, it also retained slender second and third digits, unlike its more specialized cousins. Furthermore, its teeth were not the minute, crushing teeth of later anteaters, but rather relatively large, non-serrated, and pointed, suggesting it was an active pursuit predator, hunting smaller insects and perhaps even tiny mammals, rather than specializing in ants. Its vision and hearing may have been as sharp as those of owls, further enhancing its predatory capabilities in low-light conditions.
This find was a paleontological Rosetta Stone, fundamentally breaking the previous model of Alvarezosaurid evolution. It revealed that extreme miniaturization in this lineage did not necessarily co-evolve with the specialized digging arms or tiny teeth for crushing ants and termites. Instead, it seems that miniaturization preceded these anatomical specializations. Becoming tiny was an earlier, more general adaptive step that then enabled these dinosaurs to later advance into the specialized niche of eating social insects. This suggests that miniaturization was not a singular linear march towards an extreme endpoint, but rather a more complex and messy evolutionary process where body mass fluctuated repeatedly, with some individuals achieving their small size independently. For Anachetri, being small meant being fast and agile, like a roadrunner, allowing it to actively hunt its prey in a dynamic ecosystem. This agility and access to smaller prey would have been a significant survival advantage, opening up ecological opportunities that larger predators couldn't exploit. The impact of this discovery extends even further, reshaping our understanding of where Alvarezorids lived and when. Before Anachetri, it was a mystery why these dinosaurs were found almost exclusively in the late Cretaceous rocks of Asia and South America. The leading hypothesis was a late-stage dispersal between these continents. However, placing Anachetri, a remarkably basal member of the group, into their evolutionary tree created a massive ghost lineage. Phylogenetic analysis suggested that geographically close South American species were linked to much older, geologically distant Asian taxa, implying that the group must have diverged much earlier, perhaps as far back as the Jurassic period. To fill this chronological and geographic gap, paleontologists delved into historical museum collections, re-identifying fragmentary theropods from the Upper Jurassic Morrison Formation in North America and a Lower Cretaceous taxon from the Isle of Wight in Europe as early diverging Alvarezorids. These re-identified fossils possessed specialized ball and socket joints in the neck vertebrae that are unique in the Alvarezorid clade, strengthening the argument for their placement.
These re-identifications completely changed the biogeographical story. It now appears that early alvarezarids were widespread across the supercontinent Pangaea before it fully fractured, with their later, more restricted late Cretaceous distributions being the result of populations becoming isolated as the continents drifted apart, combined with regional extinctions. Thus, miniaturization not only unlocked new dietary strategies, but also allowed for a broader initial geographic spread, offering more opportunities for survival through diversification.
Moving beyond the theropods, miniaturization also played a crucial role in the survival strategies of plant-eating dinosaurs. From the early Cretaceous of northern Spain, a recent discovery introduced us to Phascea pellendonum, a small-bodied herbivore. The name Phascea means light foraging in Greek, reflecting its likely ecological role, and pellendonum honors the Pellendones, a Celtiberian tribe from the region where it was found. What's particularly significant about this find is that through meticulous examination of its fragile skull using microcomputed tomography, microcourt, to allow for digital assembly without damage, and osteohistology on its limb bones, researchers confirmed that the largest specimen had already reached sexual maturity. The presence of slowdown lines near the outer surface of its bones indicated it was a fully grown adult, not a juvenile of a larger species. This definitively established its small size, just over half a meter in length and weighing less than 10 kilograms, as a result of evolutionary miniaturization. Histological research even hinted at a surprisingly active biology, with a high metabolic rate similar to modern birds or small mammals, a significant physiological insight for a small herbivore.
Phascea was no miniature version of its larger plant-eating relatives. Its skull revealed unique anatomical innovations. The front of its upper jaw was fused into a single solid section, and some of its teeth pointed slightly forward, altering how its jaws met when it bit down. These unexpected traits show it had its own specialized anatomy, adapted to its diminutive stature. Its teeth and limb proportions suggest that Phascea fed close to the ground, likely on tough plants, and relied on quick sprints to evade danger. Its hips and legs indicate a posture that changed as it grew, allowing for bursts of speed through dense forests where tight spaces favored agility over sustained long-distance running. Its specialization in diet and locomotion, facilitated by its small size, allowed Phascea to carve out an ecological niche in environments inaccessible or unsuitable for larger herbivores. Its existence helps fill a significant 70 million-year gap in the fossil record of Rhabdodontia, a European branch of plant-eating dinosaurs, demonstrating that evolution was experimenting just as radically at small body sizes as it was with large ones, creating unique adaptations for survival.
Even further back in time, to the mid to upper Triassic of Madagascar, another astonishingly small creature, Konganofan-Kelly, which translates to tiny bug slayer, offers profound insights into the very origins of dinosaurs and pterosaurs. This ornithodiran archosaur, recovered as a member of the Triassic ornithodiran clade Lagerpetidae, expands the range of this group into Africa. Standing at an estimated mere 10 centimeters tall, it is one of the smallest non-avian ornithodirans ever described, and crucially, it was confidently diagnosed by the authors as a non-paranate, meaning it was a grown individual, not a hatchling or very young individual. Its conical teeth bore pitted microware, a clear indicator of a diet consisting of hard-shelled insects. This shift to insectivory, a trophic ecology associated with its diminutive body size, was a critical survival strategy. The discovery of Konganofan-Kelly highlights a profound miniaturization event that occurred near the common ancestor of dinosaurs and pterosaurs, suggesting it was a foundational step for entirely new evolutionary pathways, including the later evolution of powered flight and fuzzy body coverings. The extreme rarity of early ornithodiran fossils has historically obscured our understanding of this crucial period.
But Konganophan suggests that this rarity might be more a matter of taphonomic artifact, the difficulty of preserving such tiny, delicate bones over millions of years, rather than a true reflection of their abundance in ancient ecosystems. This tiny ancestor demonstrates how miniaturization could be a foundational step, opening up entirely new evolutionary pathways and survival strategies for entire lineages. The extreme rarity of early ornithoderen fossils has historically obscured our understanding of this crucial period, but Konganophan suggests that this rarity might be more a matter of taphonomic artifact, the difficulty of preserving such tiny, delicate bones over millions of years, rather than a true reflection of their abundance in ancient ecosystems. This tiny ancestor demonstrates how miniaturization could be a foundational step, opening up entirely new evolutionary pathways and survival strategies for entire lineages.
And sometimes what we thought we knew about miniature dinosaurs turns out to be a case of mistaken identity, which in itself yields invaluable new insights into survival strategies. For over 2 decades, paleontologists debated the identity of dozens of unusually small armored dinosaur fossils, each less than 40 centimeters long, unearthed from the Cretaceous of Liaoning Province, China. These specimens, known as Liaoningsaurus paradoxus and initially described in 2001, were preserved in extraordinary detail in a shallow lake covered by volcanic ash. They were initially thought to represent a bizarre miniature species of ankylosaur, fully grown adults that simply never attained the massive, tank-like proportions typical of their relatives. Speculation abounded, with some even suggesting a semi-aquatic lifestyle for these pint-sized armored creatures. However, a recent, comprehensive study finally brought clarity through the power of osteohistology, the microscopic analysis of bone structure. By carefully examining thin slices of their bones, researchers discovered a crucial absence: no visible growth lines. This indicated that all the Liaoningsaurus specimens were less than 1 year old at the time of their death. Furthermore, in the smallest fossil, a delicate hatching line was identified, a tiny ring-like feature laid down in the bone at the moment an animal emerges from its egg. This confirmed that Liaoningsaurus paradoxus was not a miniature adult species, but rather a collection of hatchling ankylosaurs, some barely out of their shells. This reinterpretation provides incredibly rare and valuable insights into the earliest developmental stages of armored dinosaurs. As paleontologist Paul Barrett noted, "As we have found so few fossil babies, Liaoningsaurus is really the only good window we have into what Ankylosaurus are like just after they hatch." It challenged previous assumptions that Ankylosaurus developed their heavy armor plates relatively late in life as a response to increasing size and predation risk. Instead, the Liaoningsaurus hatchlings already showed signs of armor, suggesting that protective features were essential and present very early in their lives, providing a vital survival mechanism from their most vulnerable moments. This discovery vividly illustrates how even the smallest, most puzzling fossils, when subjected to advanced scientific scrutiny, can unlock profound secrets about dinosaur biology and their diverse adaptations for survival. This discovery vividly illustrates how even the smallest, most puzzling fossils, when subjected to advanced scientific scrutiny, can unlock profound secrets about dinosaur biology and their diverse adaptations for survival.
These recent discoveries, from the fast-hunting alnachetri to the ground-foraging Foschia, the insectivorous Konganophan, and the armored hatchling Liaoningsaurus, paint a vibrant picture of miniaturization as a dynamic and multifaceted evolutionary strategy. They show us that shrinking wasn't a single uniform process, but a series of diverse adaptations that allowed different dinosaur lineages to overcome environmental challenges, exploit new resources, and evade predators. These tiny dinosaurs weren't just smaller versions of their larger kin. They were uniquely adapted, often innovative creatures whose survival hinged on their ability to master the small. But understanding that they shrank is only part of the story. The next crucial question is how they managed this incredible feat on a developmental level.
Chapter 3. Growth's Hidden Lever, Dinosaur Size. We've marveled at the diverse forms of miniature dinosaurs and the ecological niches they conquered. But understanding that they shrank and why it was advantageous leads us to an even more fundamental question. How did they actually do it? For a long time, the scientific community held a strong, almost axiomatic belief about how animals evolved changes in body size. The conventional wisdom was that an animal primarily achieved a larger size by simply growing faster than its ancestors, and conversely, smaller animals grew slower. This idea, rooted in observations across many animal groups, suggested that the rate of growth was the predominant developmental lever influencing an animal's ultimate stature. However, the groundbreaking Demick et al. 2023 study into non-avian theropod dinosaurs is now revealing a much more complex and surprising story, fundamentally challenging this traditional view. Their sophisticated comparative analyses have discovered that changes in the duration of an animal's growth played an almost equally significant role in shaping dinosaur body size as changes in the growth rate. Imagine that. It wasn't just about how quickly they grew, but also about how long they kept growing, or how quickly that growth was curtailed. This concept, known as heterochrony, refers to shifts in the relative timing or rate of developmental events. While the acceleration or deceleration of a rapid growth phase was long considered the primary mechanism, scientists are now finding that the prolongation or truncation of this growth phase, essentially a change in how long an individual grows before reaching its adult size, was just as crucial. This new perspective provides a deeper understanding of the biological mechanisms that allowed certain dinosaur lineages to shrink, often dramatically, to survive and thrive. To uncover these developmental secrets, paleontologists turned to an incredible natural archive, the bones themselves. Like tree rings, bones preserve annually deposited growth marks, or cortical growth marks, which act as a biological timeline. By analyzing these marks, scientists can estimate an individual's age and growth rate. This meticulous process involved examining approximately 500 annually deposited cortical growth marks, CGM, from more than 80 skeletal elements of 42 non-avian theropod dinosaur species, encompassing a vast range of body sizes, from tiny chicken-sized creatures to massive apex predators. To uncover these developmental secrets, paleontologists turned to an incredible natural archive, the bones themselves. Like tree rings, bones preserve annually deposited growth marks, or cortical growth marks, which act as a biological timeline. By analyzing these marks, scientists can estimate an individual's age and growth rate. This meticulous process involved examining approximately 500 annually deposited cortical growth marks, CGM, from more than 80 skeletal elements of 42 non-avian theropod dinosaur species, encompassing a vast range of body sizes, from tiny chicken-sized creatures to massive apex predators. What emerged from this extensive dataset was truly unexpected. Researchers found no straightforward, consistent relationship between an animal's maximum annual growth rate and its ultimate adult body size. This means the old axiom that larger animals always grow faster and smaller animals always grow slower simply doesn't hold universally for theropod dinosaurs. For instance, the truly gigantic Majungasaurus was found to have grown remarkably slowly, even slower than modern alligators. Conversely, some of the smaller dinosaurs exhibited incredibly fast growth rates, comparable to those seen in today's rapidly maturing mammals. This decoupling of growth rate and final body size highlights that simply growing faster wasn't the only or even the primary path to gigantism, and shrinking wasn't solely about slowing down growth. Instead, the critical factor often lay in the duration of their growth period.
Bigger animals might have grown for a longer period during their growth spurts, reaching immense sizes over many years, while smaller animals might have truncated their growth, reaching sexual maturity and ceasing growth at a much younger age, regardless of how fast they grew during that shorter period. This revelation has profound implications for understanding the miniaturization of dinosaurs, as it provides a new lens through which to view the adaptations we discussed earlier. The peculiar alverosaurids, a group of bird-like theropods, offer a compelling example of miniaturization driven by altered growth duration. While their extreme small size is often associated with specialized diets, research into late Cretaceous Asiatic Parvicursorinae revealed that their miniaturization occurred by shifting ossification to earlier ontogenetic stages, notably the premature closure of neurocentral sutures in juvenile animals. This was a fundamental change in their developmental schedule, shortening the period over which their bones would typically grow and mature, leading to smaller adult sizes. This mechanism, rather than simply a slower growth rate, allowed for their dramatic size reduction. The plant-eating dinosaur, Phascea pellendonum from Spain, provides another example of evolutionary miniaturization, achieved through a truncated growth duration. The long-standing debate over Nanotyrannus, whether it was a distinct, smaller species or a juvenile Tyrannosaurus rex, has also been clarified by focusing on growth duration. This indicated a shorter growth duration to reach its adult size compared to its massive cousin. The emerging picture from this research is that evolution is far more creative in shaping body size than previously understood. It's not just about turning the dial up or down on growth speed. It's also about altering the biological clock, the timing and duration of developmental processes. This understanding opens up exciting new avenues for investigation into the molecular and genetic mechanisms that regulate growth, revealing the intricate dance between developmental biology and evolutionary change, and offering insights into the diverse life history strategies that allowed dinosaurs to thrive. Chapter 4: Bones' Hidden Story: Growth and Shrinkage. Having explored the diverse forms and ecological advantages of miniaturized dinosaurs and the critical role of growth duration in their evolution, as discussed in previous chapters, we now delve into the scientific detective work that underpins these discoveries: osteohistology. This microscopic examination of dinosaur bones, akin to reading the tree rings of ancient forests, has been instrumental in unlocking the precise developmental strategies that allowed theropod dinosaurs to shrink and, crucially, to survive. Osteohistology is a powerful tool in paleontology, allowing researchers to peer inside fossilized bone tissue and reconstruct an animal's life history. Bones, much like trees, lay down annual growth marks, often called cortical growth marks, as their growth slows or pauses with seasonal changes. By preparing thin slices of these ancient bones and examining them under a microscope, paleontologists can count these rings to determine an individual's age at death. The spacing between these rings reveals how quickly the animal grew. Widely spaced rings indicate rapid growth, while narrowly spaced ones suggest a slower pace. Furthermore, the presence of an external fundamental system, tightly packed growth lines near the outer surface of the bone, is a telltale sign that an animal had reached skeletal maturity, and its rapid growth phase had significantly slowed or ceased entirely. This microscopic evidence is invaluable, offering a direct physical record of an animal's developmental journey, allowing scientists to distinguish between a fast-growing juvenile and a truly miniature adult that has completed its growth cycle. For instance, the adult status of the tiny Triassic ornithodeiron Conganophan kelly, a mere 10 centimeters tall, was confidently diagnosed by osteohistology, confirming it was a grown individual and not a hatchling. This microscopic evidence is invaluable, offering a direct physical record of an animal's developmental journey, allowing scientists to distinguish between a fast-growing juvenile and a truly miniature adult that has completed its growth cycle. For instance, the adult status of the tiny Triassic ornithodira Konganafon-Kelly, a mere 10 centimeters tall, was confidently diagnosed by osteohistology, confirming it was a grown individual and not a hatchling.
Indeed, osteohistological studies have been crucial in revealing the surprising diversity of theropod growth strategies, demonstrating that changes in growth duration were often as critical as growth rate in determining final body size, a key insight explored in Chapter 3. For example, Ceratosaurus grew rapidly with plexiform neurovascular canal organization densely permeating a cortex of woven to parallel fibered bone that is interspersed with few growth marks. By contrast, the similarly sized Ceratosaurian Majungasaurus grew much more slowly, even slower than extant alligators, exhibiting longitudinal to circumferential neurovascular canal organization surrounding parallel fibered to lamellar tissue interrupted by many closely spaced lines of arrested growth.
Osteohistology has illuminated diverse paths to shrinkage, particularly within the peculiar Alvarezzosaurids, a group of bird-like theropods. Detailed osteohistological analysis on various Alvarezosaurid specimens has provided a nuanced picture of their miniaturization, moving beyond simple dietary hypotheses as discussed in Chapter 2. For instance, comparing two extremely small Alvarezzosaurids, Zixionicus Jean, showed 7 growth marks, indicating an age of at least 11 years at death, while Albinicus batar, a similarly tiny species, had only 3 growth marks. Despite their similar diminutive adult body sizes, these two animals had markedly different life histories and growth durations. Both, however, exhibited osteohistological features indicative of advanced ontogenetic stages, such as an external fundamental system or outer avascular lamellar-zomal bone, confirming they were mature adults. This reveals varied strategies even within very small taxa, some reaching their small size over a longer, slower growth period, others achieving it more quickly. In contrast, larger, earlier branching Alvarezzosaurids like Haplocheirus solars possessed fewer growth marks and complex fibrolamellar bone, signaling a young ontogenetic stage and a rapid growth rate. This suggests a pattern where growth duration was significantly truncated in their miniaturized descendants, allowing them to reach a smaller adult size. Further research on some late Cretaceous Asiatic Alvarezzosaurids specifically revealed that their miniaturization involved shifting ossification to earlier developmental stages, notably the premature fusion of neurocentral sutures in juvenile animals. This fundamental alteration of the biological clock, shortening the window for growth, led to a smaller adult body. Perhaps one of the most prominent examples of osteohistology settling a long-standing debate concerning body size involves the contentious identity of Nanotyrannus. Was it a distinct, smaller species of Tyrannosaur, or simply a juvenile Tyrannosaurus rex? This question had simmered for decades, with implications for our understanding of predator diversity in the late Cretaceous. Recent comprehensive analyses, particularly of the dueling dinosaurs fossil, finally provided definitive answers through meticulous bone examination. By studying the growth rings within the limb bones, scientists determined that the Nanotyrannus specimen, though dramatically smaller than an adult T-Rex, was skeletally mature, having lived for approximately 17 to 22 years, with 25 cyclical growth marks visible. The rings became progressively more narrowly spaced towards the outer surface of the bone, indicating that its growth was slowing down, a clear sign of approaching adulthood, not the explosive growth expected of a juvenile T-Rex. Growth modeling further confirmed that these animals would have reached a maximum size far smaller than T-Rex. Independent confirmation came from the histology of hyoid bones, which also indicated maturity. This powerful osteohistological evidence confirmed that Nanotyrannus was indeed a distinct species that achieved its smaller adult size by completing its growth cycle at a much reduced stature, a fundamentally different developmental strategy from its massive cousin. This meant 2 different Tyrannosaur lineages were pursuing distinct survival strategies side by side.
The revelations from osteohistology are continually reshaping our understanding of dinosaur biology. By meticulously examining the microscopic details within their bones, we are moving beyond mere size comparisons to uncover the intricate developmental programs that underpinned their evolutionary success, particularly their diverse strategies for miniaturization. This ongoing exploration promises to reveal even more about the hidden lives of these magnificent creatures and the molecular mechanisms that controlled their growth. Chapter 5. Miniaturization's Edge. Conquering New Niches. We've explored the profound phenomenon of dinosaur miniaturization, delved into the remarkable recent discoveries that showcase this evolutionary trend, and uncovered the intricate developmental strategies, particularly the duration of growth, that underpinned these size reductions. Now it's time to bring these threads together and examine the ultimate outcome: how this shrinking act wasn't just a survival tactic, but a powerful engine for innovation, allowing dinosaurs to conquer entirely new ecological niches and diversify in astonishing ways. Miniaturization wasn't merely about becoming smaller versions of their ancestors. It was about transforming their very existence, opening doors to lifestyles previously unimaginable for creatures of their lineage.
One of the most striking advantages conferred by miniaturization was access to a vast array of microhabitats. For the colossal dinosaurs, the world was largely a sprawling, open landscape. But for their shrinking relatives, dense understory vegetation, intricate forest canopies, and even subterranean burrows became accessible, transforming previously impenetrable environments into viable homes. This physical access was a game changer, immediately expanding their ecological real estate. For example, some small-bodied herbivores, whose adult status was confirmed through osteohistology, developed unique anatomical features that allowed them to thrive in the tight, cluttered spaces of ancient woodlands, exploiting low-lying, tough plants that larger herbivores couldn't reach or navigate. Their agility, a direct benefit of small stature, was a primary defense, allowing them to dart away from danger in environments where sheer bulk was a hindrance. This wasn't just survival, it was the active colonization of a niche defined by its small scale and complexity, a testament to how miniaturization could drive entirely new forms of herbivory.
Beyond simply accessing new spaces, miniaturization often led to radical shifts in diet, unlocking entirely new food sources and trophic levels. For many larger dinosaurs, the menu was relatively constrained by their sheer size and energy requirements. But for their smaller kin, the world of insects, small vertebrates, and diverse plant matter became a feast. An early example from the mid to upper Triassic demonstrated a profound shift to insectivory, with a diet of hard-shelled insects directly associated with its diminutive body size. This early insect-eating niche, enabled by tiny body size, was a profound ecological innovation, potentially influencing the origins of fuzzy integument body coverings in both groups, not just flight. The Alvarezzosaurids further illustrate how miniaturization enabled a cascading effect of niche specialization. In this lineage, extreme miniaturization appears to have preceded the full suite of ant-eating adaptations seen in its later relatives. Early branching forms were agile pursuit predators, actively hunting smaller insects and perhaps tiny mammals. This initial miniaturization created a general niche for small, agile predators, which then opened the door for later Alvarezzosaurids to develop unique digging forelimbs and minute teeth for a dedicated myrmecophagous niche, a diet of social insects like ants and termites, a niche that became increasingly abundant during the Cretaceous terrestrial revolution with the diversification of flowering plants and the insects that fed on them. This demonstrates how miniaturization first opened broad new categories of prey and then allowed for even finer-tuned specialization within those categories.
Perhaps the most dramatic and far-reaching evolutionary advantage of miniaturization is its undeniable connection to the origin of birds and the conquest of the aerial niche. The physics of powered flight fundamentally favors lighter bodies.
The theropod lineage, directly ancestral to birds, underwent a sustained and prolonged phase of miniaturization. This continuous reduction in size was not merely a trend, it was a prerequisite, a foundational evolutionary step that paved the way for the development of aerial capabilities. As these dinosaurs became progressively smaller, they evolved skeletal adaptations, including features like hollow bones, reduced tails, and ultimately wings. The ability to fly opened up an entirely new dimension of ecological opportunities, from escaping ground-based predators to accessing food sources in the air or high in trees, fundamentally reshaping their survival strategy and leading to an unparalleled diversification into what we know today as birds.
The recognition of Nanotyrannus as a distinct, smaller species rather than a juvenile T-Rex also highlights how miniaturization enabled niche partitioning even among apex predators. While T-Rex was a heavyweight, bone-crushing predator, Nanotyrannus was a leaner, swifter, and more agile hunter. Its smaller adult stature meant it occupied a different predatory niche. This allowed Nanotyrannus to coexist with its gigantic cousin in the same late Cretaceous ecosystems, likely hunting different sizes or types of prey, or employing distinct pursuit strategies.
This mid-sized predator niche, made possible by its smaller adult stature, demonstrates how miniaturization could lead to a more complex and diverse trophic structure within ancient food webs, enabling multiple closely related species to survive by specializing on different resources. The proliferation of miniaturized dinosaur species during the Cretaceous, particularly in the late Cretaceous, was not a random evolutionary accident. It was a strategic response to a period of intense global change. New types of forests and undergrowth habitats, for instance, were particularly suitable for smaller animals. In these dynamic and often resource-limited conditions, miniaturization, with its access to new microhabitats and specialized diets, provided a powerful evolutionary toolkit. The ongoing discoveries continue to reveal that evolutionary innovation was not confined to gigantism. It thrived equally in the realm of the small. The intricate anatomical features found in tiny dinosaurs were distinct innovations, finely tuned for survival in their specialized, miniaturized niches. This recognition compels us to look beyond the spectacle of gigantism and appreciate the profound evolutionary success hidden in the small, in the agile, and in the specialized. What further secrets do these tiny bones hold about the ultimate fate of these evolutionary trailblazers? And how might their diverse strategies inform our understanding of life's resilience in the face of planetary change? From agile hunters like Alnashetri to the direct ancestors of birds, we've seen how dinosaur miniaturization was a dynamic, recurring evolutionary strategy. It wasn't merely about being small, but about profoundly changing growth duration, unlocking new microhabitats, diverse diets, and crucial survival advantages. This journey shows us that evolution's ingenuity isn't solely found in immense scale, but often in the subtle, strategic shifts that allow life to thrive amidst changing worlds. The story of tiny dinosaurs reminds us that even the smallest changes can lead to the greatest transformations, shaping entire lineages and revealing the overlooked power of adaptation. Thank you for joining us on this exploration of the shrinking giants.